My talk today is going to be based mainly on these two recent papers with Stefan Kasper and Mendel Nguyen, who some of you may know. Okay, so, well, that doesn't work for some reason. Okay, great. Okay, so I'm interested in studying lattice regularizations of quantum field theories. So the question, of course, many of you don't need a justification for this, but why do we care about lattice regularizations of field theories? Well, certainly one important aspect is that they provide a rigorous definition of any given quantum field theory beyond perturbation theory. It can also happen that while you're trying to formulate a theory of the lattice, you understand something that was very subtle in the continuum and tricky in a much more direct way, right? That happens all the time when you're studying lattice theories. And probably the most important reason is that for strongly coupled theories such as QCD, this is actually mostly the only way to compute non-perturbative observables in a controlled manner. So then you can also ask, why do we care about studying new lattice regularization? Maybe we already know some way to regulate, say, lattice QCD. Maybe that's enough. So what I want to say is that that's actually not enough. For a given lattice regularization of a field theory, you may encounter sign problems, and you may want to solve them. So then, there's many ways to think about it. One way is to just really think about new lattice regularizations of that given theory. You may also find that when you consider a different lattice theory, you understand something in a different way, right? The symmetry structures may be different and so on. And another reason, which is kind of close to my heart, is that when you have a new lattice regularization, it may actually enable you to use new techniques, such as tensor network methods or even quantum computers. So when I use the word lattice regularization, I'll be slightly more strict about it than maybe since this is like a cross-disciplinary workshop. So for me, a lattice regularization or a lattice model is only a lattice regularization if I can take a continuum limit. If I can't take a continuum limit, it's not a lattice regularization for that field theory. So in other words, that a given lattice model needs to have a second order critical point where the correlation length diverges. If a given lattice model, which for me can either be a classical statistical lattice model, which would be, you can think of it as a Euclidean path-integral field theory, or it can be a quantum lattice Hamiltonian, that doesn't matter. But it's a lattice system which has a second order critical point, and if it has that, then I can get a continuum quantum field theory out of it. So this was Wilson's, one of many insights that near a second order critical point, you can really get a continuum limit of a quantum field theory. Okay, so to emphasize that point slightly more, when I say, so a quantum field theory from that point of view, right, is essentially an RG flow between an ultraviolet fixed point and an IR fixed point, right? So in many cases, these UV and IR fixed points are conformal field theories, and you have some kind of relevant perturbation about the ultraviolet fixed point, which makes you flow into some IR theory. And when you have a lattice regularization, it must actually reproduce the physics of the entire flow, right? There is nothing in this flow that you shouldn't be able to get out of it. And if you don't have that, right, maybe you only get like this stuff, well, then I would say that you just have some kind of low energy effective theory. It's a lattice model, but it's not really a lattice regularization.
Can I ask a silly question?
Yes.
Like, what's wrong with that last possibility as long as you do have an IR fixed point?
Well, because this is also physical, right? So like if you think of QCD, there is actual physics of asymptotic freedom there, which is real, right? So if you have a lattice model which only reproduces this stuff, there's two things that go wrong. One, you actually don't have, like, you can't make contact with some physics that exists there. And secondly, there really is no way to control it, right? You don't know if what you're measuring for that lattice model, is it real physics or is it just lattice artifacts? For you to be able to control those errors systematically, you need to be able to push that cutoff all the way to infinity, which means being able to access the UV fixed.
Actually, can I ask a question?
Yes.
The definition on your previous slide of lattice regularization.
Yes.
But by your definition, when we do the QCD on the lattice,
Yes.
is that a lattice regularization?
Yes. Yes. It is. It is because in the usual sort of most lattice field theories, I'll talk a little bit more about it. There's the coupling G.
Yeah.
And when G goes to 0, that's a second order critical point.
Okay, that's the critical point you're accessing.
Yes. Yes.
And would you then take all of this at face value and declare that no condensed matter related model could ever be viewed as a lattice regularization of quantum field theory?
Except that many condensed matter models have second order critical points. So therefore, I can
The short distance physics ain't going to be the physics of the long distance theory.
I'll talk about it. I'll talk about it. This is an important point for me, and I will yeah. Let me just go on. It'll be a lot of my talk. Okay. So to make everything concrete, let me talk about a famous toy model for QCD, which is called the O3 nonlinear sigma model. This is a 1+1 dimensional theory. We really like it because it has a lot of the fun properties of QCD. It has asymptotic freedom. It has this kind of dimensional transmutation. It dynamically generated mass gap. It also has theta vacua. So what is the theory? Well, it can be described formally by this continuum Lagrangian, where you have this n vector field at each point in space-time. This is Euclidean space-time right now. And this n is a unit vector in R3, or you can think of it as the target space being S2. And so you notice that this coupling G is a classically dimensionless coupling, right? So classically, this theory has no scale, but the usual standard story, just like QCD, is that a scale gets dynamically generated due to quantum corrections, if you want, and that's kind of responsible for, the glue ball mass and so on, right? In QCD, it's the same kind of physics here. Okay, so those are the sort of differences and similarities between SU and Yang Mills in 4 dimensions and the O3 model. Of course, many things are similar, but of course, many things are also different. Importantly, there's a local gauge symmetry, or there's a gauge symmetry in the SUN theory, whereas here, what I really have is just a global O3 symmetry, which is just the rotations of this n vector field. Okay, so this is coming back to your point, which is that it's tricky to just say low energy. You really should think of the many scales present in any given lattice system. So what happens, for example, in an asymptotically free theory, you certainly have lattice spacing, right? That's a scale which is present in your lattice system. Then you have the correlation length in a given lattice system, which is the super IR scale, right? So that's in an asymptotically free theory, it's usually an exponentially large correlation. But then there's an intermediate scale in the middle, which I'm calling here LUV. This is also a physical scale in the sense that there is real predictions made by the quantum field theory for this scale. And so it might be that if this scale is so short in terms of lattice units that is basically touching your lattice spacing, then you will sort of miss the physics here, right? You might only see this correlation length. But you want to be able to actually access all these scales. And so this physics, all of this physics here is the physics of the continuum quantum field theory, whereas this stuff is lattice argument.
So but the lattice spacing is up to you. You can just keep pushing it to 0.
If you have, you can do that if you have a critical point in the lattice.
Oh, I see.
You mean you can
So
do
there's
that while maintaining sort of physical?
Yes. So that's right. So when you say you can push lattice spacing to 0, it really only makes sense because lattice spacing again is in a way it's a physical, or you think of lattice spacing in physical units, right? So what you really are saying when you say that you're pushing lattice spacing to 0, you're saying that the ratio of A over C is going to 0. So of course we think A is going to 0, but really in the lattice model, C is going to infinity, which is the same thing as A going to 0.
Right.
But it's unclear what is exactly the definition of this UV scale in the middle. is it drastically different from infrared physics in some sense? I mean, what sets the UV physics?
Yeah, what sets the UV physics is the critical is the RG fixed point, which corresponds to the critical point that you're sitting at. So maybe I'll explain that a bit more as I go on. But the really, yeah, that's what it is, right? So for example, for QCD, the UV fixed point is the fixed point of free quarks and gluons, right? So it's just a free theory.
Well, I'm thinking, let's say QED. Is there such thing?
QED, yeah, in four-dimensional QED does not have
exactly. It will be about theory.
Yeah, so from that point of view, I can't get a non-trivial continuum limit out of that from a lattice, right? There isn't. Yeah. Okay. Okay. So to really study that model, the model that I just showed, what you can do again is to construct a lattice theory out of it, right? So you might do what you might call a naive discretization. Just start with this continuum Lagrangian, replace the derivatives by finite differences at different sites, and then you end up with a model like that, right? So this is a model in space-time on some kind of lattice, and these nx and nys are just these again vectors, unit vectors living on these things, right? So this is coming to your point that the way you raised, just like QCD, this model should have a second order critical point when G goes to 0. That's why I can define a continuum, right? So I can flip it on its head, the whole thing on its head, and I can just say, if I don't know how to rigorously define a quantum field theory, I can just say, look, start with this lattice model, take this limit of G going to 0, whatever you get, that's the O3 non-relation. Okay, so part of the reason I'm really interested in it today is that this model actually allows for a topological theta term. So again, in the continuum, it has this kind of form. You can put an I theta q, and the q is given by this kind of formula, right? And for closed manifolds, you can show that this is integer, and so theta is 2 pi quantized. In nature, of course, this is the fact that theta is really small corresponds to, or in the standard model, right? The fact that theta corresponding to the SU QCD theta is small, and that's called the strong CP problem. Okay, so the thing with theta is that the physics of theta is totally non-perturbative. It doesn't show up in perturbation theory, so you can't really understand it that way, what it's doing. On the other hand, you can say perhaps that if it doesn't show up in perturbation theory, the UV physics of the theory is unchanged, right? So if you believed that the original theory you started with was asymptotically free at high energies, well, adding theta shouldn't change that, but it can totally change the infrared physics. You just have no control over it in perturbation theory. And in fact, something very drastic does happen when you tune theta to pi, which I'll talk about in a minute. And then, of course, the question really is what happens at arbitrary theta. Okay. So this is what the expected RG flow for this theory looks like. Remember that in sort of my way of thinking about it, this entire line corresponds to the quantum field theory, right? So you have this asymptotically free UV fixed point, which is the same for theta equals 0 and theta equals pi. But then at theta equals 0, if you the theory is gapped. So there's a mass gap, so which means if you just keep flowing to longer and longer distances, eventually you would have integrated out everything there is, and you would just end up at a trivial with a trivial theory. On the other hand, at theta equals pi, the low energy physics completely changes, and what you end up with is a conformal field theory, which is called the SQ2 level 1 Western Newton field theory. Now, at intermediate theta, what is believed is that it's gapped for all theta in the middle. But of course, as you tune theta closer and closer to pi, what can happen is that the RG flow goes arbitrarily close to this point, but then eventually goes back down, right? So what's happening in a way is that there are multiple scales in the problem, multiple length scales in the problem. And there's an intermediate length scale. So there's a length scale at which the UV physics is happening. There's a large length scale, longest length scale where the correlation length is. But then there's an intermediate length scale where you will start seeing the physics of this SU2 Western innovative trading. Okay. And again, I want my lattice regulator to recover all of this, right? The intermediate stuff. Yeah.
I have a silly question. So naively in this model, there's one length scale, namely lambda QCD or lambda O3. What are the multiple length scales?
Yeah, great question. So I would say that one length scale is that signal is only true at theta equals 0. And when you introduce theta, it introduces another length scale in the problem. I will try to give some more intuition on this length scale as we go on. But you know, you can imagine, right? If it's a relevant perturbation, any relevant perturbation will introduce another length scale. So then it becomes kind of a competition in your existing length scales and what parameter or what this theta is doing.
I have a question.
Yes.
So in the lattice theory, without the theta term, we just have a G to tune. When you add the theta term, do you have to tune two couplings, or is one coupling fixed and that's pi?
Yeah,
Does that make sense?
that's a great question. In fact, that's probably one of the motivating questions of what I'm trying to say, because it's actually one way to ask that question is, does theta anomalize? And as far as I know, there isn't a clear answer to that, right? There are some papers over the years have suggested, people have suggested that, you know, theta normalizes to 0 or something, and then it doesn't even, like, these various theories don't even exist. So this will be a motivating factor for me to sort of go on this this whole route, and I'll try to answer it in a way.
Gotcha.
And yeah.
Here you fix the theta. So
Here, yeah. So okay, so I can add one more thing to that. Certainly at theta equals 0 and theta equals pi separately, you're fine, because those points are protected by a symmetry. So theta sort of it wouldn't flow, right? There wouldn't be any. And I will talk about that symmetry more. But in the middle, it's fuzzy. It's not clear. Sorry, does that?
yeah, maybe read it. Just I want to make sure on this plot you have fixed theta.
The way I'm drawing these lines, I'm imagining that there's a fixed theta, and you're kind of that there is a field theory, there is a unique field theory for every given theta, and then it would flow like this. Okay, that's the picture. Yeah, that I'm drawing. Yeah, great questions. Okay, so that's exactly this point that the theta equals 0 pi's are very special, certainly because of the symmetry, the extra symmetry that's protecting those points, but also because they're integrable. So you can actually do a lot of things there. But the intermediate stuff isn't so clear. Now, again, as I was saying, people have been worrying about this issue for a long time. I believe starting from Schwab and Lucia in '82, where there's issues like there are ultraviolet divergences if you try to compute topological susceptibility. So people have talked about how it's not a physical thing, and along the way people have just suggested that non-zero theta doesn't even make sense, so on, right? So there's some funny stuff. It's so that question, I think analytically, as far as I know, there's no handle on it. There's some lattice studies, so which I will come to in a second. But I think it's important to sort this out, right? Because if you can't do this for the O3 model, then Yang-Mills is even harder to make any concrete claims about. So now let's talk about the lattice formulation. So how would you actually go about solving this kind of question? Well, you can't just do a lattice calculation to try to see whether you're getting some universal things at intermediate theta, right? Okay, so the moment you try to do that, you first run into this issue that even in Euclidean spacetime, there's an I sitting here, which means that this theory has a sign problem. Okay, or I should say that it has, in this naive formulation, it has a sign problem. Now, if you're very clever, you can do things as these people did, and actually the theta equals pi sign problem can be solved using what they call a Miron cluster algorithm, right? So that can be done. However, for this intermediate theta, again, you run into issues. Again, they've done some very interesting things to actually make progress. And I think it's very impressive, but still it's not like you completely get rid of the problem. And in particular, you can't probe arbitrarily large lattice sizes in those techniques as well, right? So it would be great if we had a way to do this model in a completely signed problem.
I'm sorry, can I ask a
Yes.
question actually before you get into this? I'm gonna thought a pedestrian way to figure out whether this is relevant or not is to look at the 2-point function of the operator couples to theta. In other words, the topological density Q. So you could look at that 2-point function and look at how it falls off with space, right? And then like about each of the fixed points. And then we know that if it falls off quickly enough, then it's not relevant. It falls, I don't know. I got that, you get the idea. You can look at the scaling dimension of the operator Q, and then from that figure out whether it's relevant or not.
So Q is a global topological chart. I guess you're talking about the local.
The thing that you integrate, yeah. Sorry,
Yeah.
Q is integral of something, and so
I would imagine that
people done that. That seems much easier than what you're about to do.
Yeah, there should be a central, you do the computation at theta equals 0, so there's no central.
Yeah, this computation you do at theta, I think theta equals 0 is boring because it's supposed to a gap thing. Theta equals pi, it seems there's scope for something interesting to happen.
But you yeah.
And I'd be surprised because I always thought theta was exactly marginal, so I would be surprised.
Well, I think that's the thing. In this formulation, it will be almost by construction.
Yeah.
When I talk about the actual lattice formulation, you can really just restrict to in a lattice theory. You can really restrict to it given theta.
Okay.
So I'm not totally sure how you would check it. It seems inbuilt.
Right. Okay. I can.
Yeah. Let's discuss.
If someone might have done that in those references, but it sounds okay.
Yeah. Let's discuss next. I want to understand that better. Okay. Okay. So what I want to ask is there a way of completely maybe solving the sign problem and doing it in a totally different way, right? One idea, which is again motivated for me from the point of view of trying to do things on quantum computers, which is of course another way of solving sign problems, which we can imagine and dream about right now, is maybe we can formulate the whole theory totally differently, perhaps as a model of qubits, and maybe something interesting happens there that way. Right, but remember, if I do anything I do, I have to demonstrate to you that I can get this entire length, all these length scales in the proper model, right? Okay, so this story starts with Haldane in 81, I think, where he showed that if you consider a antiferromagnetic spin S Heisenberg chain, what you get at low energies is in fact the O3 nonlinear sigma model with theta given by 2 pi s, right? So if it's spin half, you would get theta equals pi, spin 1, you would get 2 pi, which is the same as 0. Okay, so this was a surprise apparently to both condensed matter and high energy communities, because condensed matter people knew that the S equals half chain was massless. So they thought that the S equals 1 chain would also be massless, but it turned out because of this mapping that is massive. Like people knew more about the theta equals 0 nonlinear sigma model. On the other hand, high energy physicists were surprised because they knew that the theta equals 0 nonlinear sigma model was massive. So they thought that nothing interesting might happen at theta equals pi. But again, this mapping showed them that theta equals pi is massless. So this was kind of a funny thing. I read this in a paper by Affleck, so I believe that that this surprise was in fact true. So
I thought the high energy people thought there would be spontaneous symmetry from discrete symmetry.
yeah, from a large n point of view, right?
Yeah.
That's I'm not sure when the large n calculations happen relative to this paper. I think,
Much earlier.
but yeah, even in that case, I think it might be. I think the early indications were sort of numerical, small lattices, and so on, just exact diagonalization type studies.
Yeah.
But yeah, that's a good question.
Is there a paper by Simon in large M CPM on the Lattice? And in that case, of course, it's gapped by what the break C in large M. But
Yes,
surprise is any complete state.
Yes. Okay, so so the question is, okay, so this, let's take that as a given, right? We know that this happens at low energies. But what I want then is to be able to take the continuum limit, which is to actually get asymptotic freedom out of this. Okay. So one very interesting way is this following, right? So consider not a 1D chain, but a 2D chain, right? So imagine that this thing has an extent L1. Okay. Now, when Lx in L and Ly both are large, that's a 2 plus 1D model, and that we know undergoes spontaneous symmetry breaking, where the SO3 symmetry breaks and reduces to SO2. So if you were looking at the spins, you would see that, okay, they're all ordered, right? They're all pointing in the same direction. This is a bit funny because the model is actually antiferromagnetic, so you should really imagine that these spins are antiferromagnetic, right? So when they're ordered, it's ordered with a negative sign on all alternating sides, right? Because they're all antiferromagnetically ordered. But anyway, so you know that there are going to be Goldstone modes and so on for this antiferromagnetic system. Now, what happens if so this is massless, right? Because you have massless Goldstone modes. Now, what happens if I make Ly small? Now, when I make Ly really small, well, it starts looking like a 1 plus 1 dimensional system, where we know, due to Coleman-Mermin-Wagner theorem, that a continuous symmetry cannot break spontaneously. So what must happen is that the system starts developing a length scale at which it starts to order. Okay, so if you look really close at really short distances, it might still look ordered to you. But now, as you're making Ly smaller and smaller, the fluctuations in these systems are becoming large relative to your lattice spacing. So, for example, in this picture, you can see that at about this length scale, the system is disordered, right? So these are the infrared fluctuations that cause the system to disorder. So this length scale is what I'm calling a symmetry restoration length scale.
Could you have a BKT type case where you have algebraic correlators and gapless modes, but no genuine symmetry breaking?
You mean in this system?
Yeah.
Well, in this system, we know what happens. Okay. But in general, yeah, like O2, I think if you were to look at the O2 model, yeah, that would happen.
I think I have basically the same question, but then asking in different words.
Yeah.
At least from a continuum intuition, you're starting with a model that has continuous spontaneous symmetry breaking 3D, right?
Yes.
Okay. Since I thought that if you compactify the model at all on any size circle,
Yes.
there's no more spontaneous symmetry breaking.
Yes.
For any size circle, not to make it small. Any size is enough to kill spontaneous symmetry breaking.
Yes.
And instead you get what Theo said, which is algebraic ordering. So, in other words, your CESR naively is divergent with Ly.
CSR is definitely divergent with Ly. So I think we're
So
actually
for any finite Ly,
for any finite Ly, exactly, the
CSR.
Goldstone modes have to pick up a mass.
yes.
That's exactly what I was
That's
going
what
to say.
you're saying.
Yes. That for any finite Ly, the system has to start to order. And the length scale at which it orders is the mass of the Goldstone.
Sorry, but just to be careful, I mean, I think it doesn't actually develop a gap. It continues to have algebraic order, I guess.
So
BKT.
why do you say that?
What's the BKT physics?
Well, so that happens with the O2 model, but this is the O3 model, right? The O3 model in 1 plus 1 dimensions, we know that it is gapped and has asymptotic freedom and so on. The O2 model, yeah, like if I were to do the whole story, the same story with O2, I think what you're saying will be true, right? I could start with, instead of, like, I could break the O3 symmetry to O2 in the original Heisenberg model, and then we would be like the XY model, right? That's where you would be exactly right. Okay. Okay, so I'm going a little bit slow, so let me try to speed up. But these are great questions. Please keep them coming. So this is an idea which sort of goes by the name of T theory. It was originally introduced by Chandrasekhar and Visa in '97, also extended to QCD using what is called quantum link models, right? So again, the idea is that you have this Heisenberg antiferromagnet, which is a two-dimensional system. But as you make Ly small, what you can show is that the correlation length actually is exponentially large in Ly, which means that actually, this should really be the CSR, properly speaking, what I'm calling CSR. And if that's really large, then the physics in the y direction is just frozen, right? It's ordered in the y direction. So that really makes it a one-dimensional model, right? So this kind of validates this idea. Okay. So the punchline of this story is that I can in fact make the correlation length large by simply making Ly, starting from Ly small and slowly making it large. The correlation length will diverge, which is exactly what I want if I want to take a continuum. Okay, so that's that. Okay. I'll get to some results very quickly, but let me just complete the story by asking, okay, it seems like I can get UV physics out of it. How to get the IR physics, right? So I started the story by saying I want a theta term. Okay, so how do I get a theta term? Well, note that at theta equals 0 and pi, the system, the original sigma model has a charge conjugation symmetry which sends n to minus n, which is broken if I change theta away from 0 and pi. Now, in terms of spin variables, really, if you think about the fact that it's antiferromagnetic, so at low energies, sort of the classical ground states look like this, right? They are antiferromagnetically ordered. So the action of sending like n to minus n really looks like a translation by 1 unit in the spin chain. Okay. So what that would mean that if I wanted to get a non-zero or non-trivial theta in the IR, which means I have to break charge conjugation somehow. Well, in the spin model, what that means is that I should break this translation by 1 symmetry that's present. As long as I have that, I will never be able to get non-trivial theta. But if I do that, then perhaps I can get a non-trivial theta. And in fact, this was shown by Haldane and Affleck, or even in their early papers, that if you start with this chain and sort of stagger these bonds with the staggering parameter, which is gamma, right? So that's the coupling. In fact, if you take some non-zero gamma, you will in fact get an arbitrary value of theta by continuously tuning down. Okay. So if you put these two things together, which is that you can get to the asymptotically free regime by making Ly large and using the idea of dimensional reduction, and you can get the theta term in the IR by just breaking charge conjugation. Well, that would suggest that you can get the full physics, right? You can start with a theta and take the continuum limit. Okay, so that's the proposal, that you consider lattices like this sort, and importantly, you keep to get to the continuum limit, you have to make Ly large, but to keep theta fixed, you have to keep this constant gamma times Ly, which is coming back to kind of your question of how the normalization of theta works. But that in this model, you keep gamma Ly constant as you make Ly large, then supposedly you get a non-trivial theta. Okay, so let me skip the details of what I'm actually measuring, but just maybe try to give an intuition here. So what I'm measuring on the lattice in a numerical calculation, which I, by the way, didn't say, the fact that this is a model which actually has no sign problem. This is an antiferromagnet. We know very well how to do Lattice Monte Carlo with antiferromagnets, non-frustrated antiferromagnets, so no problem. Well, let's do it. What I measure is, I measure the correlation length in a finite box and divide it by L, so that's my Z. And then I measure the correlation length at a box of size 2L, okay, and then I divide it by CL. Now, what this is measuring is some kind of beta function, right? Beta function measures what happens when you change, what happens to a physical scale when you change a physical length, or when you change your probe scale by the decimal amount. That's what the beta function. Well, this is just changing it by a finite amount, right? Say taking L to 2L. So L is your probe scale. This is like a beta function, an integrated form of beta function. Okay, So in this plot, what it's supposed to happen is when correlation length is very large, you're in the UV regime, or rather the box size is very small, so you're probing short distance physics. You're in the UV regime, and you're getting this. This thing is 2, which is the scale invariant, right? There's only one scale in the system when it's asymptotically free. So this should just be 2. On the other hand, this is the IR regime when the box size is so large that you're really probing long distance physics, and there it goes to 1, because at some point when you've made the box size large enough, the correlation length stops responding to it. It's a finite, it's a gap system, so you can really make L greater than CL, right? So that would just make it 1. It would stop changing. Okay. So this is actually what happens when you take the system I talked about and do a Lattice Monte Carlo's calculation. In fact, so let's first, just to guide the eyes, look at the theta equals 0 line, this dashed line, right? That's an actual calculation done with a conventional lattice model, and you find this behavior that I was just talking about, that for large Z it goes off to infinity, or it's large Z is going towards 2, so that's going to the scale invariant region. And here it's this is the trivial IR fixed point, and so it's going to 1. When theta equals pi, what you find is that it agrees with the theta equals 0 curve in the UV, but then turns at some point and goes back to 2. And that's because, again, 2 is like a beta 0 of the beta function. So it's like the beta function turning back up and hitting a conformal scale invariant point again. That's theta equals pi. And what you find when you turn on these various gamma Ly's, the staggerings, that you can smoothly interpolate between all of these curves, right? So this is kind of validating this picture that we had earlier, right? So it's completely analogous. These are in fact can really be thought of as the RG flows computed numerically for these curves. Okay. Well, this is just to say that we can also actually do really think of these things on quantum computers. So that's kind of fun. But let me not talk about that. Okay. So let me also skip that. That's just a summary of what I just spoke. Now, what I want to say in the last 3 minutes somehow is that in this picture, right, we saw that, okay, that we have a kind of a regularization, a lattice regularization using qubits for the O3 model, which completely solves the sign problem. But it somehow depends on this kind of thing where you have the staggering and you get a theta term out. Okay, so what we wanted to explore was whether you can understand this in some way, right? Can you generalize this idea to other kinds of field theories? And so this was the work that I did with Mendel recently. The point of the paper was that of course, we know that symmetries are very important in constructing lattice regularizations, but an interesting constraints and insights can come from also considering anomalies. Now, it's true that we want a lattice regulator to preserve all the continuum symmetries. That it's just nice when that happens. But when some symmetries have this more subtle structure, which we call an anomaly. So let me define what I mean here by an anomaly. So in this talk, I'll only talk about atrophed anomalies, and the definition of an atrophed anomaly is that G, if G has an atrophed anomaly, what that means is that G is a genuine global symmetry of the theory, but it cannot be gauged. Okay, there's some problem in gauging. That's an atrophed anomaly for G. A somewhat refined notion of an atrophed anomaly is when you have a mixed atrophed anomaly. So that just means that there's two symmetries, G1 and G2, which are both genuine global symmetries. They cannot be, well, they can be gauged individually, but when you gauge one, you break the other. So that's like saying that there is a atrophed anomaly for G1 cross G2, and you can't gauge both of them simultaneously. Okay, so classic example is the U1 axial times U1 vector symmetry of a free Dirac formula in 3+1 dimensions, where the standard story is that, as we all know, is that if you break or if you gauge U1 vector, you lose U1 axial in a precise way, right? And we learned a lot more about that from Nabil earlier in the workshop. So So that's for the U1 vector axial for grad fermion. What happens in this system that we're talking about? It was noticed by these authors a few years ago that at theta equals pi, there's in fact a mixed anomaly of a very similar sort between SO3 and charge conjugation. Okay, SO3 is just the usual rotations, global rotations, or in the integral space, and charge conjugation is phi over this phi. So again, if you gauge phi, or if you gauge SO3, for example, you will lose charge conjugation. Okay, so somehow the fact that there's an enhooped anomaly must be reflected in the regularization, the lattice regularization. To make that statement a bit more precise, I'm probably out of time. Right.
You could probably take a few minutes.
Okay, maybe I'll try to quickly finish this. Yeah. Well, to make this statement a bit more precise, you can assume a lattice regulator for a QFT with a symmetry G such that it's the same space-time dimensionality. The symmetry is exact, it's local, and it's on-site. Okay, so the on-siteness is important to me. What that means is that the symmetry action factorizes over the local Hilbert spaces, right? So if you have some sites, then the symmetry acts on each site individually, right? So that's the full action. Now, when you have on-site symmetries, you can just always gauge them. That's the trick of lattice field theory. That if you have a lattice model with on-site symmetries, you can always gauge them by introducing link variables. But if you have an anomaly of the sort that we were talking about, then there must be some obstruction to this procedure on the lattice, right? And that's sort of where almost this lore comes from, which is, a lot of times you will sort of hear people say that there are no anomalies on the lattice. Okay, so one way in which this obstruction might occur in the actual system is that the symmetry is just not on site, right? This is something that's very well appreciated in condensed matter literature. That whenever you have some anomaly in the continuum, it's manifest. It's the way that symmetry is manifested on the lattice is that it's on off-site. Indeed, that's what happened in the spin chain we were talking about, right? That this was off-site, which was crucial for us to get a theta term and get a sign problem-free formulation. But now we can see that this off-siteness wasn't an accident. It seems like it was almost forced by the anomaly. Okay, so that's great. But what if you really insist that your lattice model has an on-site symmetry, right? So, a case in point, consider the standard latticeization that we started with. In this model, both SO3 and charge conjugation are on-site. It's just the usual action of n going to minus n, for example. And for this model, a topological theta term on the lattice was defined very early on by Berg and Lucier, which also maintains this property of SO3 and C being on site. It's very elegant. It just says that you consider a triangular lattice, and then three vectors sitting on the edges of it or the vertices of it form a spherical triangle. Compute the area of the spherical triangle. That gives you your local charge density. Just sum it up. That's your topological charge. You can show that it has all the nice properties, such as being quantized and so on. So if it is true here, right, that the symmetry is both exact and on-site on the lattice, what goes wrong? Why can't you gauge it? Well, you can gauge it, and you find that it actually just reproduces the anomaly. So there is, in a way, no obstruction beyond what you already know from the continuum, that you just actually get it on the lattice, right? And the procedure to see it is quite identical or analogous to what you do in the continuum. You introduce some background gauge fields for, in this case, the SO3 symmetry, and you just do a C rotation and find, or C transformation, and find that the partition function is not invariant. So that's completely identical. Okay, so I'm sort of coming towards the end. So the main point that I want to convey is that from this construction, right, this kind of lore that that there are no anomalies on the lattice, that's an incomplete lore. In fact, recently there have been many more examples of anomalies on the lattice. And in fact, Theo also gave this nice construction for a Chern-Simons theory, which also exhibits an anomaly for a one-form symmetry. Although it might seem somehow that some of these recent formulations have this are talking about this modified Villain formulation, and might seem at first glance that maybe this is something special to Boolean formulations, but it's actually, I think, not, right? It's just the fact that you have an on-site symmetry, and then you can't escape having an anomaly on the lines. Okay, so this sort of gives you a dichotomy between, it seems like there's this dichotomy for like lattice regularizations on the lattice, where, you know, on the one hand, you have this exact anomaly, which is manifestly topological in this Berg-Lucia theta term, but it has sign problems. On the other hand, when you implement it using this kind of qubits, you have this symmetries offsite. You know, it's not manifestly topological, the theta term in that, it's given by this gamma. But on the other hand, it has no sign problem, and it's very natural for quantum computers also. So it seems like, okay, this is just a generalization to, you know, other theories, which is also fun. Let me skip it. Yeah, to summarize, it seems like there are really different kinds of regulators which are different by how the anomaly is manifested on the lattice, and they're really different, right? They have different advantages, and it depends on what kind of question you're asking if you want to study one of them. And there's interesting parallels also with 4D non-abelian cases that would be very interesting to explore. So maybe I'll just conclude with this slide here and not say more. Thank you.
So what do you mean when you say like theta equals pi on the lattice? Because it's obvious what that means in the continuum, but is there a coefficient of reaction which looks like pi, or you get your relation like?
No, it's actually exactly that. You just, oh, when in the spin chain example.
Yeah.
In the spin chain example, that's a great question, because the way we do it is, let me go back somewhere. So yes, okay, here. Yeah, so you see that it's really so it's this coefficient is 2 pi s ly, right? So imagine you have qubits, so s equals half, which means what you have is pi ly, which means if ly is odd, then what you're getting by tuning gamma is just always a deviation from pi. So what I really do is I just do odd ladders for theta equals pi, and even ladders for theta equals 0, and then I can choose either of them if I want to interpolate between them.
And then one more question. So you take a continuum limit by taking an infinite volume, but by taking ly big?
Yeah.
That's right?
Yes.
Got it.
So for this formula, so you basically derive it following the original Haldane derivation of classical Schumann formula.
Yes.
And in that sense, so as Nabil pointed out, so since we believe that this classical formula is rigorously correct, so theta is just a marginal perturbation.
This formula is rigorously correct. You're saying this formula is rigorously correct?
Yeah.
This is
Isn't it what you make a computation suggest?
the numerical computation suggests, what it suggests is the following. I wouldn't say that this formula, well, yeah, it's hard to say. So what the numerical computation suggests is that at least for large Ly, this becomes more and more exact, right? So when I'm taking the continuum limit, the continuum limit is at large Ly, right?
Okay.
But for really a finite ladder, there's always going to be like largest artifacts.
Okay.
And so I wouldn't, yeah.
But still by choosing choosing gamma, so you do not suffer from ultraviolet divergence, right? So
There's no ultraviolet.
So at least in the leading order level, this formula. So your result follows.
Yes, I mean, yeah, I believe after seeing the results that indeed I can get a fixed theta if I keep gamma Ly fixed.
Yeah, and doesn't that observation suggest that theta is a marginal operator?
Yeah, okay, yeah, fair. Yeah, exactly. Okay, good, thanks. Yes, I agree. That's exactly the point I want to, yeah, I mentioned it, but this does suggest that indeed there's a unique field theory for, every theta.
Okay.
Right? This is a way of getting to those. So these curves in the middle are universal curves. If you had full analytic control over the quantum field theory, you should be able to directly compute this curve. In fact, this dotted line is a perturbative calculation, right? So that's just the beta function. So that can, if you know the first few beta function coefficients, you can get this this dotted line here. So that's all agreeing, right? The question is, can you get all of this from some other method? And if you can, then you have two different methods to really say, okay, yes, everything is agreed.
Okay, thank you. Yeah, I just wanted to confirm your answer.
Yes, thanks for bringing that up. That is indeed an important result that I should have said. Yes.
So why did she have a sign problem? Like, was that just an accident or?
Yeah, frustrated antiferromagnets people have figured out how to do it. So I'm just using the knowledge, I think. Sorry, did I say frustrated? Non-frustrated. Frustrated antiferromagnets will still have a sign problem, but non-frustrated antiferromagnetic magnets we know how to solve. So yeah, I mean, I'm using some whole line formulation here and Bohm algorithms, so these are very efficient. We know how to do these things.
All right. Could you remind me what is this correlation length?
Yeah, that's also a good question. This is actually an interesting observable itself. It's supposed to, so it's given by this.
How do you define that?
This is the definition.
Okay.
So you measure, what you're measuring is some kind of, so G0 is just the, so you measure the Green's function, 2-point function in Fourier space. So G0, which is just susceptibility, right? And then you measure it at the one higher, the first momentum level. So that gives a second moment of the susceptibility. And then you construct this kind of observable by taking these ratios. So what you can show, this is like an ansatz really. It's what you can show is that this, for let's say a free theory corresponds exactly to the correlation length. You can also show that in the large volume limit, it corresponds to the usual correlation length.
Oh, sorry. What do you mean by usual?
Oh, usual correlation length. So the point of this definition is that a correlation length is strictly defined for an infinite system, right? Because you want to see the follow-up behavior at large distances. But if you put the system in a finite box, what is the correlation length? So this is a definition of so the infinite volume correlation length is something which is uniquely defined. And then for a finite system, you can come up with your definitions, but you have to make sure they agree, with certain kinds of things.
Then, and also you mentioned the relation to the Goldstone energy mode math.
Yeah, I think here. I think that this.
Oh, okay, but yeah, anyway, I could learn the definition.
So
and also, and you said, to take continuum limit, you need to have some like a Zygote infinity.
Yeah.
Is that independent from the asymptotic?
Is it independent?
So yeah, question is if every time this asymptotic we have some Zygote goes to infinite, is it always or not?
Yeah. So it's a good question. This is to do again with we should be. So C going to infinite is always necessary when you're taking the continuum limit. Okay, so that is a true fact that you always need. Now, so it has nothing to do with asymptotic freedom from that point of view. The reason it's related to asymptotic freedom is that asymptotic freedom is a high energy phenomena for these field theories, right? These are not free all the way; they're only free at very high energies. So you have to be able to take the continuum limit to really probe the physics of asymptotic freedom. And so even in fact, when I say in these plots, right, that the fact that this beta function was computed perturbatively, this dotted line, right? So that was computed perturbatively using asymptotic freedom in the analytically, and that only agrees here when the correlation length is very, very large, right? So you make the correlation length large, or you make the box size small relative to the correlation length. That means you're probing short distance physics, and that's when. So in that sense, they're related.